Hi geometry students, this is Miss Graham, and today we are going to be looking at lesson 15-2, rectangles, rhombuses, and squares. Go ahead and pull up page 216. Now today we're going to go through the first half of the notes, and then tomorrow in class we're going to go through the second half of the notes. Let's look at our learning targets for today. We're going to start to develop properties of rectangles, rhombuses, and squares, and we're going to start to prove properties of these three quadrilaterals. So, a rectangle is a parallelogram with 4 right angles. So given quad RECT as a rectangle below, we're going to start off by listing the right triangles in the figure. We're going to list them instead of explaining how we know the triangles are congruent. So let's go ahead and start off with REC. So I'm going to start off by listing that as triangle. I should probably close the other side of it. So we have triangle REC. We're going to say that is congruent to our next triangle. Let's say we'll do TCE. So we know it's congruent to triangle TCE. And then we're also going to say it is congruent to triangle ERT. So it's congruent to triangle ERT. And then last but definitely not least, we're going to look at triangle CTR. So it's congruent to triangle CTR. Now again, you don't have to follow the exact same letter order, but make sure that you are able to address all 4 of these triangles that we have here. All right, let's keep going on to number 2. It wants us to complete the theorem. It says the diagonals of a rectangle are, and what we're going to learn is that they are congruent. Now, if we look down below, it says for us to explain how we know the theorem in number 2 is true. Well, keep this in mind that we know all of these triangles are congruent, and don't we know that the diagonals are corresponding parts of the congruent triangles? So that's how we're going to go ahead and answer. We're going to say the diagonals are corresponding parts of congruent triangles. Nice. All right, let's go ahead and go down to number 4, where it says list all the properties of a rectangle. Begin with the properties of a parallelogram. So that's something we saw in our notes yesterday. So we're going to go ahead and build off of that while looking at what we know today. So something that we could start off looking at is each of the opposite sides of a rectangle. Well, we know that they're actually going to be congruent and parallel to each other. So let's write down opposite sides are congruent and parallel to each other. Now, the next part that we're going to look at is our diagonals. What we learned before is that our diagonals actually cut each piece in half. So the diagonals bisect each other into congruent parts. So we're going to go ahead and write down diagonals bisect each other and are congruent to each other. Now, the last piece that we're going to look at is something we know about rectangles already. It's the 4 right angles, right? We create right triangles, so there has to be a right angle. We're going to look at it without the diagonals, but we're going to say that the angle measures, so we'll start off with angle measures 90 degrees. And are all congruent. So angles measure 90 degrees and are all congruent to each other. All right, so we got our list of properties of a rectangle. let's go ahead and cross out number 5. We're going to skip that, and we're going to scroll down and start to look at number 6. So right here, we can see we're given quadrilateral TGIF, and we see it's a rectangle. We're going to use the properties of a rectangle we just wrote down and the figure to find the following. So let's start with part A, where it starts giving us different angle measures. So it says TX is equal to 13. So I'm going to label that on my picture, and it wants us to find what TI is, that whole length. Well, keep in mind, TX is the same as TI, so the whole length is going to be 26. Now, if we look at our other diagonal, right, we know actually FX will also be congruent to TX. And we know XG will be also congruent to FX, which is congruent to TX. So we know that this whole length of FG will be the same as this whole length of TI. So we know that's going to be 26 as well. So we can go ahead and put congruence tick marks on those lengths too. Now, looking at part B, we can still use the same idea where all of these lengths are congruent to each other, but now we're going to use different values. So we're not going to have 13 anymore there. We're going to apply what we now have. So now we want to solve for x if tx is 4x plus 4. So instead of labeling it 13, we're going to label it as 4x plus 4. And it also gives us fx, which is 7x minus 23. So remember what we learned before is that for each of these segments, we can set them equal to each other. And we're going to try to solve for x here. So what I'll do is I'll start by moving 4x over to the right side. I will get x on the right side this time. So we have 4 equals 3x minus 23. And then I'm going to add 23 to the other side. So I have 27 equals 3x. When we divide by 3, we end up getting x as 9. So solving for x, we can get x equals 9. So I'm going to see if you can try to set up part C. We're looking at the angles now. So see if you can remember kind of what we know about our rules of rectangles and see if we're able to apply something for part C. So go ahead and pause the video right here. So for part C, I started to list what I had on our picture here. So we know that this angle right here is 6x minus 4, and we know this angle right here is 10x minus 2. Now if we had both of these angles right next to each other, we know they would add to 90 degrees. So we kind of have to think about what information we have. Well, looking at our picture, we know that this is an isosceles triangle, correct? So we know that its base angles are going to be congruent. So we know these two angles are congruent. Well, that's pretty helpful because now we know that this angle is 6x minus 4 and this is 10x minus 2, so we can add them together to get 90 degrees. So that's what our equation is going to be for part C. So it's going to be 6x minus 4 plus 10x minus 2, that's going to equal 90. So let's start to combine like terms. So we got 16x, and we're going to combine our negatives, so it's going to be minus 6 equals 90. We're going to add 6 to both sides, so we get 16x equals 96. And then we're going to go ahead and divide by 16. So we will get x equal to 6. So for x, we're going to get it to equal 6. So you can tell that a lot of these rules for quadrilaterals build off of what we've learned previously, maybe about triangles or maybe even about angles. So keep those things in mind. We're going to go ahead and turn to the next page. Now, we're really not going to talk about too much on this page, but I did want to bring an idea up at the top of indirect proofs. Just keeping in mind that indirect proofs can be useful when the conclusion is a negative statement. So if we're ever trying to prove something is maybe not a rectangle and we're giving pieces of information do not match. That's just an example of indirect proof. We're really going to focus on direct proofs. So we can go ahead and skip past this page and go to page 218. So now that we're on page 218, we are going to go ahead and zoom in to number 10. So let's go ahead and look at number 10. Here we have another quadrilateral that we're being introduced to, a rhombus. We're going to see a rhombus is actually a parallelogram, but with 4 congruent sides. So we're going to go through number 10 and start to examine more properties of this type of shape, but we're also going to experiment a little bit by using a coordinate plane. Now we're going to have to refer back to finding different slopes. So something we saw probably in your Algebra 1 class last year, so keep that in mind. It wants us to start off by graphing the quadrilateral USMC with the following coordinates. So go ahead, graph it on the grid below, and then press play when you are done. All right, I was able to graph my points, so now we want to connect them. Oh, let's try that again. We want to connect them to make our parallelogram. All right, looking good. Now here's what it wants us to do. It wants us to verify that this quad is a parallelogram by finding the slope of each side. Well, we're not sure what that's going to yield to yet, but let's go ahead and figure out what the slope is for each one of them. Now, remember, slope, right, is rise over run. So let's start off looking at side US. So we know our rise, how much we go up by is 1, 2, 3, 4. And we know our run is 1, 2, 3. So we know that our slope, when we're looking at US, so the slope of US is going to be 4 over 3. Now what's nice is if we look at CM, the slope of CM, you're going to see the same pattern. We go up 1, 2, 3, 4, and then go over 1, 2, 3. So we know the slope of US and the slope of CM is going to be 4/3. Now we also want to make sure that we're looking at the slopes of our other line segments as well. So let's look at SM. So we're going to try to figure out what the slope of SM is. Well, thinking about this, it doesn't rise anything. It goes up 0, goes over 1, 2, 3, 4, 5. So we know 0 over 5 is going to yield a slope of 0. Same thing's going to be our slope of UC. So we're also going to get 0 as well. So I'm going to go ahead and put in the slopes. Oop, let's try that again. I'm going to put in the slopes of, and it's probably good for us to include the line segments above each of those lines. I probably should have done that ahead of time. That's all right. So we know the first one was 4/3. And we also know SM and UC is going to be 0. Now, here's the trickier part. For part B, it wants us to verify that USMC is a rhombus by finding the length of each side. Well, what's nice so far is if we look at what we had for our horizontal lines, we can count the lengths, right? That's so easy. So we know that the length of UC and of SM, we know that's going to be equal to 5. But remember, we can't count diagonals, right? We have to figure out a different approach to this. So there's 2 ways that we could do this, and I will show you both ways. And just to let you know, it's a nice reminder. It's a nice reminder of what we've done before. So think about if we're trying to find the distance between 2 points, aren't we using that distance formula, right? So we're looking at the coordinates of S, which is 4, 5, and of U, which is 1, 1. So that distance formula, right? That distance formula is going to be the square root of our x values subtracted and squared minus our y values subtracted and squared. Now, which x value and y value are we subtracting first? It honestly doesn't matter as long as you keep the order the same. So I'm going to put my 1's first. Now, when you label the points, it also doesn't matter which one you label as the 1's or the 2's. I'm going to label my 1's as my s value and my 2's as my u value. So let's plug in what we have. So my x1 value is 4. I'm going to subtract 1, square it, and oop, we're not subtracting that, I apologize. The formula is that we're adding the differences. So make sure you make that change. So now we have our y values. I'm going to do 5 minus 1 squared. So looking at this, we have the square root of 3 squared plus 4 squared. So looking at this, we have the square root of 9 plus 16. Hey, we're taking the square root of 25. Look at that. Don't we get a unit of 5? We do. So we do also know that the length of US will be 5. Now, we could do the exact same thing to find the length of CM, but I also wanted to review another way that we can find length. So either one of these works, you pick your fancy. So thinking about this, couldn't we change MC to be the hypotenuse of a right triangle? We could. So looking at this, couldn't we use Pythagorean theorem? Right, because we can easily count the distance here, 3, we can count the distance here, 4. So we know for Pythagorean theorem that if we square each of the legs and add them together, we get the hypotenuse squared. So we're really doing 3 squared plus 4 squared equals c squared. So we got 9 plus 16, oh, let me try that again, 16 equals c squared, so we got 25 equals c squared. Hey, guess what? We take the square root. Look at that. We also get 5. So both ways are which we can approach to showing the lengths of US and MC also equal 5. So we just verified that USMC is a rhombus because all the side lengths are congruent to each other. So we could essentially put tick marks on all the sides now that we were able to prove that. Whew, all right, we're doing a lot of work, but we're doing well. All right, let's keep going. We're going to scroll down and start to look at part C now, where it wants us to find the slopes of our diagonals. Oh boy, so we actually probably maybe have to draw the diagonals first. So I'm going to go ahead and draw the diagonal for UM. And for finding the slope of that, right, we count our rise 1, 2, 3, 4, and then our run 1, 2, 3, 4, 5, 6, 7, 8. So really, the slope for UM, so the slope of, they say MU or UM, it doesn't matter, right, is 4 over 8, which reduces to 1/2, right? So now we're going to go ahead and find the slope of our other diagonal. So let's connect S and C. So we're going to find the slope of SC. So again, we count our rise over a run. I'm going to start up here just in case we're trying something a little different. I'm going to go down 1, 2, 3, 4 over 2. So really it's -4 over 2. So it ends up being -2. So looking at this, we can see we got a slope of 1/2, we got a slope of -2. Now the reason for us to practice the slopes up here was for us to remember how to find the slopes down here, because this piece down here, right, what we have on part C, that is the crucial part that's going to help us go to part D. It says use the results of part C to complete this theorem. We're going to have some connection with the diagonals of a rhombus. What we're going to realize is, look at them. What do you notice about their slopes? Aren't their slopes opposite reciprocals? Oh boy, I know. That's what we're going to notice. Opposite reciprocals. That means they are opposite signs, right? One's a positive, one's a negative. And they're reciprocals, so we flip the numerator and denominator. So what we know out of this is that when we have slopes of opposite reciprocals, what we realize is that our diagonals are going to intersect at a 90-degree angle. So what we're going to see is that the diagonals of our rhombus are perpendicular. Whoa. So that's something that we're always going to look at and see. So that's what's special about our rhombus right here. So let's go ahead and look at number 11 below. So number 11 says that we're given quadrilateral EFGH is a rhombus. So it wants us to list 3 triangles within a rhombus that are congruent to triangle HXE. So congruent to triangle HXE. I'm going to give you the opportunity to go ahead and fill that in right now. Make sure you're listing them in the correct letter order as well. All right, let's go ahead and check. You should have gotten triangle HXE is congruent to triangle FXE, which is congruent to triangle FXG, which is congruent to triangle HXG. Alrighty, nice job. Let's look at part B, where it says explain why angle EFX is congruent to angle GFX. So let's go ahead and mark those with congruent symbols. So that's angle EFX, and this is GFX. Now we're also going to have to explain why angles HGX is congruent to angle FGX. So I put down the congruence tick marks, but something else that you want to keep in mind is that we're distinguishing them different from the other angles. So I'm going to put 2 congruence tick marks there as well, so we can see that. So go ahead and take the opportunity now to prove that, or think about why those angles are congruent to each other. So here's the big kicker. Because before we listed that the triangles are congruent, we know that corresponding parts of congruent triangles are congruent, right? That's C, P, C, T, C. So once we know the triangles are congruent, we can show that the corresponding parts are also congruent. So that's pretty cool. All right, let's go ahead and look at part C. So it wants us to complete the theorem. It says each diagonal of a rhombus. Ooh, okay, so we have to connect maybe what we saw up here with angles with the diagonals of a rhombus. So think about this. Our diagonal of a rhombus, think of what it does with this whole entire angle. Doesn't it bisect the angle, right? Both halves are congruent to each other. Now think about this. It's going to be the same on the other side too. Right? We're going to see that. So both of our angles are bisected here. They're actually opposite from each other too. Remember, opposite means they're not next to. So the same thing's probably going to happen here, right? This diagonal bisected this angle. So we know for angle H, it was also bisected as well. So what we can do is we can say that each diagonal of a rhombus, we can say bisects a pair of opposite angles. So that's another rule that we learned as well. Now, the statement that we have below this, talking about a formal proof, we're going to go ahead and cross that out. We're not going to pay attention to that. But we're going to look at part 12 now, where it wants us to list all the properties of a rhombus. And we're going to begin with the properties of a parallelogram because it builds off of that, what we saw yesterday. So let's go ahead and write some of these down. So what we're going to see is that opposite sides are parallel. That's going to be our first one. And we're also going to say opposite sides are congruent. We learned right now that the diagonals bisect each other. And we also learned that our diagonals are perpendicular to each other. That's what we learned above. And last but not least, we know all sides are congruent. So what we can do right now is we can go ahead and start looking at that family tree, where we can start to look at the rectangle and a rhombus to start to look at those rules. So I'm going to go ahead and pull that up right now. All right, we can see I literally pulled it up here. We can see we've already gone through trapezoids and isosceles trapezoids, right? So we can go back and look at those if we wanted to, right? Sometimes I like to color coordinate to see which ideas we've gone through already, which ideas build off of each other. Remember, all of these are stemming from the top. This quadrilateral, we looked at no parallel sides, one pair of parallel sides, and then this is what we've been looking at the past couple of days, looking at parallelograms. So let's go ahead and color that. We've had the rules for that where we have two parallel sides. That's why it's called a parallelogram. And then if we keep building down, right, we have our rectangle and our rhombus. So let's go ahead. I'm going to find some colors for that. So we have our rectangle here, where we saw that we do inherit some of these rules up above. It inherits the quadrilateral rules and the parallelogram rules. And then it has its own rules right there. And then something else that we saw as well is our rhombus. That's a pretty deluxe one, right? Where we see it inherits, again, the rules up above, and then it also has its own rules here. So what we're going to do tomorrow in class is we're going to continue on. We're going to review the rhombus a little more since there are a lot of properties, but we're also going to look at the square. So tonight your teacher is going to assign you some homework. I know for my class, our homework is actually we're going to be given 2 days to work on it. So go ahead, check what that is on the calendar, and have a great rest of the day. Happy mathing.